Morning to everyone. I'm going to present my thesis, which is called The Development of a Framework for Coupled Aerostructural Optimization of New Generation Wings that I'm developing under the supervision of Professor Andrea Cini and Rauno Cavallaro. The motivation is given by the need to reduce the impact of human flight on the environment. This can be done by improving the efficiency of the aerostructures. In particular, this leads to wings which are more flexible, lighter, and with a higher aspect ratio. This causes an increase in the difficulty in solving the aerostructural optimization problem. And so the objective is to devise a procedure and a tool in order to carry out aerostructural optimization relying on high-fidelity models for new generation of flexible wings, obtaining meaningful design data since the first design stages. And the majority of the research is on the structural tool. The framework overall is the gradient-based with the sensitivities computed through the adjoint method assisted by algorithmic differentiation. The architecture is composed by SU2 as a CFD solver and an in-house software called Augusto, written in C++, that performs the finite element analysis. Then there's a sprite module to exchanging information between the fluid and the solid mesh, and the Python wrapper, which drives each phase of the optimization, and that allows to exploit the Python algorithm for optimization. In the last year, I validated the framework for structural optimization in case of linear structural analysis with the structural model made of beams and design variables and the response from the aerodynamic side. Then I exclusively focused on the structural solver, implementing a geometrically nonlinear shell element that still must be improved, and implemented the adjoint structural solver for nonlinear finite element analysis. Concerning the state-of-the-art related to the structural sensitivity analysis, the first meaningful applications of the adjoint method on aircraft structures and automatic differentiation in structural sensitivity analysis dates back to the first years of the 90s. The most recent research I found employ the automatic differentiation for topology optimization and shape optimization. And I couldn't find the application for size optimization, which is what Augusto is expected to do. Then I will describe now the adjoint structural solver, the way in which we compute the sensitivities. It's based on a procedure, a fixed point iteration procedure, assisted by algorithmic differentiation through the library Codipack that was devised for aerodynamic shape optimization and is implemented in SU2. We start from the minimization problem in which we want to minimize objective function subjected to the convergence of the structural residual. We rewrite the problem in its equivalent form in which we introduce the primal structural fixed point iterator that a convergence when evaluated in the structural displacement must be equal to the structural displacement themselves. And also we have a set of structural design variables. Then we introduce the Lagrangian, so we join the objective function and the constraint in a single expression through the adjoint of the state variables, and we exploit the Karush-Cantaker conditions, obtaining the state equations, the adjoint equations, and the optimality conditions, where the last two blocks are needed for getting the sensitivities. In the solver, the procedure is the following. First of all, we solve the primal problem, so we get a converged solution. Then we select the inputs, the state variables and the design variables. We run an additional iteration of the primal solver, and we select the outputs, the newly updated state variables and the objective function. These steps are carried out while Codipack is recording. That is, we store the computational graph between the inputs and the outputs that will be needed to compute the derivatives. Then we solve the adjoint equations and optimality conditions, where the adjoint equations are solved in a way which resembles fixed point iteration procedure. At convergence, we get the converged adjoint variables that can be used to obtain the total derivatives of the response. The partial derivatives in this block are computed thanks to the fact that Codipack stored the computational path. The test case I used is a flat plate with a uniform thickness of 5 millimeters. We define 5 distinct property cards in order to have 5 distinct design variables. The response is the aggregated foam stress on this orange area, where the aggregation function is the Kessler-Meyer-Steinhauser function. The first test we made was on verification of the discrete sensitivities against the centered finite differences. We got good results in terms of percentage relative error, and the deflection was 20% of the plate length. Then we started some experimentation on some experiments on the memory footprint. First of all, I checked the ratio between the memory needed for the adjoint and the memory needed by the primal problem. The ratio is more or less 5, which is coherent with what I could find in the literature, and the peak in memory is needed for storing the computational graph. Then, through the software Valgrind, I could plot the amount of memory needed over time for all the processes, and here just for one process. The peak corresponds to the adjoint when the adjoint is solved. And at the peak, we could see that 1/4 of the memory is needed for the linear solver. The majority, almost half, is needed for storing information about the Jacobian. And there's some 1/3, more or less, which still I have to make the breakdown of this part of memory and check if it is possible to reduce it. To conclude, in the last July, I could present part of the work to the Arobes conference in Lisbon. And concerning the next steps, we will do further testing on how the code scales with the number of processes and the memory footprint. Then I'm also gathering data and already writing a paper for publication. Then we will validate the overall framework with coupled aerostructural sensitivities in case the finite element analysis is nonlinear. And the plan for next autumn is to go on a research stay at the chair of scientific computing in Kaiserslautern, in order to study and apply adjoint and automatic differentiation strategies to eigenvalue problems, and to do sensitivity analysis for the aeroelastic instability on set speed. Thank you.